Hello, colleagues. First of all, I would like to thank the Volga Bank for inviting me over at this BER conference. I've been introduced, Vadim Filippov, that's me, and today I'll just say a few quick words about our research agenda on the artificial intelligence systems creation, which may come out in 18 months approximately. So that's a startup I represent. It was established in the end of 2014 with the Rosnano and T-Platform company involved. We are only tackling neural network technologies. We have approximately 60 people on our team. We've been developing quite reasonably. We started to remain in the market, provide commercial solutions for banks and industrial companies, regional authorities, and we only just supply neural network solutions of different kinds, and we started having dozens of times growth. Last year we have gone through the second round of investments. We have attracted private investments with 45% interest rate annually, and would just like to show you a few examples of the virtual consultant on state authority services and the informer that we have launched recently all across the board, which would reply to 400 questions regarding coronavirus. 2 weeks ago we handed over a big-scale project with 10,000 questions for Sibur Holding, explaining everything about the products and services, taking orders, accepting orders.
There are multimodal cognitive systems that understand speech, video, and image. That's what we have now. But today I would just like to talk about the future, as Mikhail said. And this is my first slide. So what's in store for us? Global warming in the area of artificial intelligence, or is it going to be the first summer to be followed by another winter? So, curious question. The first summer, as you all know, was determined by the development of several architectures. A convolutional network, automorphic networks that are taught on a small number of examples. So these technologies provide for the three basic functions: classification, clusterization, and entity identification. They already allow us to build exciting products. I've already mentioned them: image recognition, multimodal systems, as I said. But at the same time, I believe that all these systems have a limitation, a principle that we need to overcome. These systems require retraining, changing the data set. That takes a lot of time. They can't, change their reasoning on the fly. These systems can't think logically, whereas in a number of cases we'd like them to. These systems don't have subjectivity. Maybe it's not that important, but that's quite interesting in certain cases. So I would now like to talk about a research agenda. So what problems do we see and trying to solve them? Firstly, we'd like to teach networks to learn very fast, not just in a small number of examples, not just long-shot learning, but on the fly, as the conversation goes, to restructure the networks to understand the counterpart. We used neurons, and it's important, I think, that we are modeling the frequency of the potential activity. There are electrical pulses accumulated. The more the charge, the higher the discharge to the next neuron. The choice of different mediators through the synaptic gap where they meet with the receptor molecules. There are very few of them. But when the charge has accumulated at the input of the second neuron, the genes fire and this is already the foundation for permanent memory. So through milliseconds, the network can restructure immediately as the conversation goes, so you don't need to retrain it in a new data set. The next task, we'd like to get rid of data sets at all. We need the networks to look at the world just like a kid does, so that they should read books and understand what's written there. For that, networks should be able to build semantic attractors on their own, themselves. And we developed special corticomorphic networks. So what's the principle? Some new signal arrives, new word, new order, new image. It goes down the cortex, and there's no pyramidal cell that's available to decode the signal. So novelty neurons get fired, and they add a huge electrical charge to it. When the signal comes back to target the pyramid, the signal is captured immediately. That's about how it happens in human brain. One other moment. When people remember something, it seems to us that we're remembering it. But in fact, the brain is recombining this information in dozens of ways, structurally through replacements and and a whole set of other ways. So this recombination, associative recombination method allows the brain to synthesize new knowledge. And so this problem of synthesis as an associative recombination is what we reproduce in our artificial cortical column. Machine logic. You know that there are 64 main figures, of which 19 are productive, providing accurate knowledge. And today we have an idea of the neural net architecture that can reproduce that. In artificial networks, it's logical thinking, and we're working seriously on that. So these approaches, as we believe, will allow us at some phase to put together an artificial quasi-cortex, where there would be a verbal zone, verbal cortex, visual cortex, and bimodal cortex. We'll be able to draw what has been said to us, or the other way around, to describe what we've just seen. But in addition to dual modality, you can add another one, and you get this artificial cortex consisting of modalities. An important problem is to see how networks are making decisions. So we're working completely 100% in our own software environment, where we can, like for instance, CAS Codifica is mentioned here, where we can use graphs, and the neurons can get images, sound, descriptions. The system can manage 3D models, or just run as a chatbot. An important point, hypomorphic networks. There are place cells and time cells. Today we reproduce that in our networks. We can show in a virtual environment, we show to the car, turn left, turn right, and then the car will drive that way regardless of the curve radius, because it not only looks at the place and time cells. We don't only quantize different visual objects, but we build the neuron of the picture as a whole. And this allows us to understand where we are. That's basically the place neuron. And we reproduce that in our today's system. So there's also a time cell that creates systems of space and time orientation for an artificial personality. Another important point, and again, it's capacity of a hypomorphic network. There's a cycle. Firstly, the signal gets amplified, then attenuates, and as a result, subjectively important information, the one that we either repeatedly see during the learning or the one that has been reinforced from the motion 90% stays with us. It's kind of a Kalman filter, whereas less important information gets forgotten. So you can even learn languages using this mechanism. The fastest way for learning the children happens, for learning the language happens with children. And this has to be reproduced in artificial systems. Today, from our experiments, we can see that we don't only see those 19 syllogisms that are known to us from human, but new forms, non-human. Being non-human, it doesn't mean that they're useless. So actually developing new ways of thinking is also something that we need to work. Unfortunately, I'm very much limited in time, so I have to speak very briefly, but nevertheless I understand and get my idea. Another point, archetypomorphic networks can grow and degrade. So, for instance, pyramid are captured, the pyramid starts processing some data, so initial networks can be destroyed, millions of connections can go away, but if the stock of cells is depleted, then cybergenes, and by the term cybergenes we name software code that allows us, a cybergenetic system can even cross among themselves. So we can turn regular cybergenes into dominant ones, and dominant cybergenes can easily pass to the posterity through such crossings. Especially of interest is that these graphs can be translated into the process architectures. There are, teachable nanomaterials that appeared, memristas, and judging by everything, the first non-living memory mechanisms are about to appear. So these are the networks that not only are defined by the software code that we build in TensorFlow, but that have graphs with physical process implied, and they can be moved directly to the CPU. And here's the essence of the race. Memristas are there, but now it's important to understand which graph architectures can be brought to the architecture of the process. Colleagues, one little point in conclusion. Machine subjectivity. Or imagine you meet a person whom you think is good, and he says about somebody else, that guy's good. If you despise this person and he says that, they say that it's a good guy, you'll probably think that he's as good as you. So the problem is that modern DNA doesn't understand what's good and bad, and don't have a predefined position of the subject. But the solution here would be to use neural networks to differentiate. Colleagues, in conclusion, I'd just like to say that we're very much concerned that AI technologies should be used for the good. And here, in these two slides, I'm listing the global goals that I believe needs to be pursued. I think we're so enthralled with such things as health diagnostics, or third opinion machines, cognitoma analysis, new molecule analysis, genomics. So AI systems can create a stronger and stronger system. In business, of course, it's about enterprise or corporate informers, industry solution, voice control, and a whole other areas. In society, basically, it's about predictive management, when we know what people want, what they write, and even before they become upset about something, we create a practical agenda to solve these problems. National informers, systems that it takes to ask, and they will respond. For instance, we recently brought several large systems into one, and it all worked quite well. And so we'd like that the development of AI systems should serve the society for the better. And that's why one of our mottos is AI for the good of the people. I would like to wrap up here, and I would anxiously wait for your questions.